Good evening. Exercise 8.1, question 5. Test the continuity of the following functions at the points or intervals indicated against them. First one, f of x is root x minus 1 minus x minus 1 raised to 1 by 3 upon x minus 2 for x not equal to 2. F of 2 is given to be 1 by 5 and we have to discuss continuity at which point? At x equal to 2. F of 2 is given to be 1 by 5. Limit extends to 2, f of x equal to this. Now you have to be very careful. Usually we put x equal to 2 plus h, but here I have put x equal to 1 plus h. So as x tends to 2, h will tend to what? 2 minus 1, that is 1. So this becomes, let me explain. Limit h tends to 1. Now x minus 1 is h, root means raised to half. So h raised to half minus h raised to 1 by 3. Now x is 1 plus h minus 2, that is h minus 1. Now in the numerator, subtract 1, add 1. Then split numerator. Now this is of which type? Limit x tends to a, x raised to n minus a raised to n upon x minus a. What is the answer? N a raised to n minus 1. Use that result. So you will get half minus 1 by 3, that is 1 by 6. Now from 1 and 2, it is clear that limit x tends to 2, f of x is not equal to f of 2. So function is discontinuous at x equal to 2. Second, f of x is x cube minus 8 upon root x plus 2 minus root 3x minus 2 for x not equal to 2. And f of 2 is minus 24. We are asked to discuss continuity at x equal to 2. F of 2 is given to be minus 24. Now, value of the limit. Rationalize denominator. Now, denominator becomes x plus 2 minus in bracket 3x minus 2. If you open the bracket, you get minus 2x plus 4. Take minus 2 common. I'm talking about denominator to get x minus 2. What are the factors of x cube minus 8? X minus 2, x square plus 2x plus 4. Can we cancel x minus 2? Yes, we can. In fact, this is giving 0 by 0 form. We can cancel because x only tends to 2. X is not equal to 2. So x minus 2 is not equal to 0. And then next part is simple. Limit of product, product of limits. So value of limit comes out to be minus 24. So from 1 and 2, limit extends to 2, f of x is f of 2. So function is continuous at x equal to 2. Now next part is types of discontinuities. A function f will be discontinuous at x equal to a if any of the following conditions is not satisfied. F of a is defined. There a function f will be continuous. They should say a function f will be continuous at x equal to a if any of the conditions. I'm sorry, this is correct. If any of the conditions is not satisfied, right? F of a is defined. Limit extends to a plus fx and limit extends to a minus fx both exist, and limit extends to a plus fx equal to limit extends to a minus fx equal to f of a. Let us classify the types of discontinuities. If limit extends to a minus fx is not equal to limit extends to a plus fx, that is, if limit extends to a, fx doesn't exist, then we cannot redefine the function f at x equal to a so as to remove the discontinuity at x equal to a. Remember, value of function at a point can be redefined, but we cannot define value of the limit, right? So if this limit does not exist, then the discontinuity can never be removed, and therefore it is called as irremovable discontinuity or jump discontinuity. Now there is one more possibility for function to be discontinuous, that limit exists but it is not equal to f of a, right? So in that case we say that function is discontinuous, but this discontinuity is removable. How to remove this? We redefine the function f at x equal to a as what? It should be equal to limit extends to a of the function f of x. I repeat, suppose value of the limit is 7 and f of a is given to be 11. So clearly they are not equal. So function is discontinuous. But this discontinuity can be removed. How? By redefining f of a as 7, same as value of the limit. As these two values become equal, the function becomes continuous. And therefore, it is called as removable discontinuity. A function f is said to have an infinite discontinuity at x equal to a if limit extends to a plus fx is either plus or minus infinity, or limit extends to a minus fx is plus or minus infinity. Example, f of x 1 upon x has infinite discontinuity at x equal to 0. Right? Then continuity in an interval. This is again important. A function f, actually there are two types of intervals, so we have to discuss continuity in two intervals, open interval, closed interval. A function f is said to be continuous in an open interval AB if it is continuous at every c belonging to open interval AB, that is at every real number c between a and b. Just a minute. Okay. Second definition is for closed interval. A function f is said to be continuous in a closed interval AB. This is quite logical. If, number one, f is continuous in the open interval AB, that is at every real number c between a and b. Then f should be continuous to the right of a. Why only to the right of a? Because elements or numbers to the left of a, they do not belong to this interval. So limit extends to a plus fx must be equal to f of a. And the third condition, limit extends to b minus f of x must be f of b. That is, f should be continuous to the left of b. So if these three conditions are satisfied, then we say that function is continuous in the closed interval. Sixth question. Identify discontinuities for the following functions as either jump or removable discontinuity. Jump discontinuity means irremovable discontinuity. First one, f of x equal to x square minus 10x plus 21 upon x minus 7. Okay. Clearly, this is a rational function. It is continuous for all x belonging to set of real number, except at the point or points where denominator vanishes. That is, in this case, x minus 7 equal to 0. That is x equal to 7. So f of 7 is not defined, so that f is discontinuous at x equal to 7. Now, what is limit extends to 7 f of x? What are the factors of numerator? They are x minus 7, x minus 3. We can cancel x minus 7. So value of limit comes out to be 4. So limit extends to 7 f of x exists. If we define f of 7 to be 4, f will be continuous for all x belonging to R. So the discontinuity is removable. But for that, we have to define f of 7 as what? Value of the limit, which comes out to be 4. Actually, in this case, if limit doesn't exist, then answer in that case will be, as limit does not exist, the discontinuity is irremovable. Second, f of x is x square plus 3x minus 2 for x less than or equal to 4. F of x is 5x plus 3 for x greater than 4. Now, what is left hand limit? 26. I hope you can easily identify which function is to be considered. X tends to 4 minus doesn't mean minus 4. It means to the left of 4 means less than 4. For that, this function. So 26, right hand limit 23. F of 4 does exist, but here you will notice that left hand limit is not the same as right hand limit. So limit doesn't exist. As limit does not exist, function as irremovable or jump discontinuity at x equal to 4. Third is for homework. Answer is it has jump discontinuity at which point is given? At minus 3. Okay. Fourth one, f of x is 4 plus sin x for x less than pi equal to 3 minus cos x for x greater than pi. What is the value of left-hand limit? For that, we have to consider which function? 4 plus sin x. Sin pi is 0. So left-hand limit is 4. What about right-hand limit? For that, we have to consider which function? 3 minus cos x. Cos pi is minus 1. So right-hand limit is 4, same as left-hand limit. So limit extends to pi, f of x exists and is 4. Now pi doesn't belong to the domain of this function initially. But if we define function f at pi as 4, same as value of the limit, function becomes continuous. Remember, limit cannot be defined. Limit is to be evaluated. So this discontinuity is removable. Sum number 7. Show that the following functions have continuous extension to the point where fx is not defined. Also find the extension. First one, f of x is 1 minus cos 2x upon sin x for x not equal to 0. Clearly, f of 0 is not defined. What is limit extends to 0 f of x? 1 minus cos 2x is 2 sin square x. Can we cancel sin x? Yes, we can. X only tends to 0. X is not 0. So sin x is not 0. Now take limit. Sin 0 is 0. So value of the limit equal to 0. So if we define f of 0 as 0, f will be continuous at x. I'm sorry. F will be continuous at x equal to 0. Therefore, continuous extension equal to 0. That is f of 0 equal to 0. And therefore, if we define fx as f of x equal to 1 minus cos 2x upon sin x, x not equal to 0, f of x equal to 0 for x equal to 0, then this function is continuous at x equal to 0. Second, f of x is what? 3 sin square x plus 2 cos x into 1 minus cos 2x upon 2 into 1 minus cos square x, x not equal to 0. Clearly, f of 0 is not defined. Let us evaluate limit. What is 1 minus cos 2 theta? 2 sin square theta. Divide numerator and denominator by sin square x. It is allowed. Why? Because x only tends to 0. X is not equal to 0. So we can take the limit now. Cos 0 is 1. So it is nothing but 7 by 2. So if we define f of 0 equal to 7 upon 2, f will be continuous at x equal to 0. So what is the continuous extension? In example, please write the complete word continuous. So continuous extension 7 by 2 means f of 0 is 7 by 2. Third, for homework, what is third one? F of x is x square minus 1 upon x cube plus 1 for x not equal to minus 1. So the extension is continuous extension. F of minus 1 is minus 2 by 3. Sum number 8. Discuss the continuity of the following functions at the points indicated against them. F of x is root 3 minus tan x upon pi minus 3x, x not equal to pi by 3, equal to 3 by 4 for x equal to pi by 3. And continuity is to be discussed at which point? Pi by 3. Okay, so f of pi by 3 is given to be 3 by 4. Let us evaluate the limit. Obvious substitution is x equal to pi by 3 plus h. As x tends to pi by 3, h will tend to 0. So limit h tends to 0, root 3 minus, what is tan of alpha plus beta? I have directly written this, tan pi by 3, which is root 3 plus tan h upon 1 minus root 3 tan h. Denominator pi minus 3 into, in bracket, pi by 3 plus h. Open the bracket to get this. Now, what is LCM? 1 minus root 3 tan h. So what is numerator? Root 3 minus 3 tan h minus root 3 minus tan h. So denominator is minus 3h. This goes to denominator only. So the next step, this is limit h tends to 0 minus 4 tan h upon minus 3h into 1 minus root 3 tan h. So this is 4 by 3 into limit h tends to 0 tan h upon h into this limit of product of limits. This is standard limit, its value is 1. Here we replace h by 0, tan 0 is 0. So value of the limit comes out to be 4 by 3. So from 1 and 2 it is clear. that limit extends to pi by 3 fx is not equal to f of pi by 3. So f is discontinuous at x equal to pi by 3. A second one is difficult one. F of x is e raised to 1 upon x minus 1 upon e raised to 1 upon x plus 1 for x not equal to 0. And f of 0 is given to be 1. We have to discuss continuity at x equal to 0. F of 0 is given to be 1. Okay. Now limit extends to 0 minus. F of x is limit extends to 0 minus e raised to 1 upon x minus 1 upon e raised to 1 upon x plus 1. See, we consider h as very small but positive number. So I write this as limit h tends to 0 e raised to 1 upon 0 minus h, because 0 minus means to the left of 0. H is very, very small but positive. So 0 minus h is definitely to the left of 0. Same in the denominator. So this is limit h tends to 0 e raised to minus 1 upon h minus 1 upon e raised to minus 1 upon h plus 1. Use laws of indices. E raised to minus 1 upon h is 1 upon e raised to 1 upon h. Right? Now take the limit. 1 upon 0 tends to infinity. So this is 1 upon infinity which tends to 0. So limiting value is 0. So 0 minus 1 upon 0 plus 1. So it is just minus 1. Now from 1 and 2, limit extends to 0 minus fx is not equal to f of 0. See, we are just asked to examine the continuity. So there is no need to find right hand limit. We just say that limit extends to 0 minus fx is not f of 0. So function is discontinuous at x equal to 0. Third is for homework. Here you will notice that limit extends to 0 f of x is f of 0, which is square of log 2 upon 2. I hope you won't write this as 2 log 2 by 2. This is not log of 2 square. Log of 2 square is 2 log 2, but this is square of log 2. Cannot be simplified further. So function is continuous. Given function can be written as square of 2 raised to x minus 1 upon 2 sine square x divided by x square and so on. Sum 9. Which of the following functions has a removable discontinuity? If it has a removable discontinuity, redefine the function so that it becomes continuous. First one, f of x is e raised to 5 sin x minus e raised to 2x upon 5 tan x minus 3x for x not equal to 0, equal to 3 by 4 for x equal to 0. And we have to discuss continuity at x equal to 0. F of 0 is given to be 3 by 4. Let us evaluate limit. First step, subtract 1, add 1. Now, index must be fully repeated. So first, we write what we want, but then we multiply by same. Here we have divided by 5 sin x. So we multiply by this. Now sin x requires x in the denominator. So effectively, we have divided numerator and denominator. Rather, we have to divide numerator and denominator by x. Okay. See, 5 sin x gets cancelled effectively upon x. Here also 2x into 2. So effectively, I have divided by x only. What about denominator? 5 tan x upon x. Minus 3x upon x is minus 3. You have to justify operation division. X only tends to 0. X is not equal to 0. And therefore division is valid. Now rearrange the terms. So 5 into limit of this. Index is fully repeated. Index tends to 0. So value of this limit is 1. Again, this is standard limit. Its value is 1. Value of this limit is also 1. Same is for this. Limit of constant is constant. So what is the value of limit? 3 by 2. It is not same as f of 0. So function is discontinuous at x equal to 0. Somebody is saying, please show the previous step. Okay. This is the previous step. I already explained this. Now limit exists, but is not same as f of 0. So it is true that function is discontinuous. But this discontinuity can be removed. How? By redefining f at x equal to 0 as f of 0 equal to value of the limit, that is 3/2. So that function will be f of x equal to e raised to 5 sin x minus e raised to 2x upon 5 tan x minus 3x for x not equal to 0. And f of 0 is 3/2. Yes, this function is now continuous at x equal to 0. Now third one, f of x is 3 minus 8x raised to 1 upon 8, rather 3 minus 8x upon 3 minus 2x raised to 1 upon x for x not equal to 0. Okay. Now within bracket, take 3 common from numerator and denominator and cancel that. So we get this. We are evaluating limit of the function. Now a upon b raised to m is a raised to m upon b raised to m, laws of indices. Now which logic? Something is added to 1. Before that, limit of quotient is limit of numerator upon limit of denominator. Something is added to 1. Same thing tends to 0. So required index is reciprocal of this. Remember, this is required. This is not original. Original is 1 upon x. So to get that original index back, raised to minus 8/3. See, effectively we have written the same, and we have to rather a raised to m raised to n is a raised to mn. Same in the denominator also. Now value of this limit is e. Same is the value of this particular limit. And therefore, e raised to minus 8 upon 3 upon e raised to minus 2 upon 3. Reason, as x tends to 0, both of them tend to 0. And limit, it is better. Yes, they have used different variable. Limit alpha tends to 0 of 1 plus alpha raised to 1 upon alpha equal to e. So value of limit is e raised to minus 2. F of 0 is not defined. So initially we have to say that f is discontinuous at x equal to 0. But this discontinuity is removable because limit exists and is finite. So we redefine the function f as follows to make it continuous at x equal to 0. F of x is 3 minus 8x upon 3 minus 2x raised to 1 upon x for x not equal to 0. And f of x equal to e raised to minus 2 for x equal to 0. So that's it for today.